Right, let's just jump straight into this. Did you know that flight delays cost the US economy a staggering $33 billion every single year? It's a massive number. But here's the truly surprising fact. The root cause of this incredible financial drain isn't just a thunderstorm sitting over one specific airport. It's actually about how those localized delays spread through the entire interconnected aviation network, almost exactly like a highly contagious virus. Welcome to this overview of SkyRipple, where we're going to show you exactly how we are completely transforming the way we understand and model flight delay propagation using advanced big data engineering.
Look at this quote from the research. It really hits the nail on the head. We absolutely have to stop looking at a delayed flight as just a single, isolated run of bad luck. Instead, we have to view it as a contagion. A disruption at one major hub simply doesn't stay local. It instantly starts cascading through aircraft rotations and crew schedules, eventually snowballing into billions in system-wide costs and massive passenger headaches.
Picture this. You have a single initial disruption, say a bad winter storm at Chicago O'Hare. It starts small, but it immediately begins infecting connected regional hubs. Literally within hours, that localized weather event has triggered a network-wide disruption across the entire United States. It just ripples outward, directly impacting hundreds of downstream flights that never even got close to Chicago in the first place. So, what's the actual problem here? Well, traditional aviation tools analyze these delays in complete isolation. They basically just count delayed flights, which means they miss this propagation effect entirely. And right now, there is no existing open-source system out there that combines real-time streaming, advanced graph analytics, and strict data privacy to solve this. Fixing this massive blind spot is absolutely crucial for airlines trying to optimize their schedules, for passengers just trying to get home, and for the FAA trying to maintain a resilient national airspace. To actually tackle this, we grabbed the Bureau of Transportation Statistics on-time performance dataset. Now, to properly stress test the big data architecture we were building, we didn't just throw everything at it at once. We structured this massive dataset into 3 scalability tiers. We started small with a Tier 1 validation set of 540,000 records, then moved up to a Tier 2 benchmark of 3.5 million, and finally pushed the whole system to the absolute limit with a Tier 3 full-scale test of 7.2 million raw flight records. Guys, the sheer scale and complexity here are just wild. We are talking about 12 full months of continuous flight data. That's 7.2 million individual records that would easily break traditional analytical tools because of the massive volume and the intense network interdependencies you need to process them. Yet, through some really efficient engineering, we compress that massive 7.2 million record beast down to a tiny 126 megabyte footprint using the columnar parquet format. Okay, so how do we actually process all that without breaking everything? Let's walk through the SkyRipple architecture. This is a real-time distributed big data pipeline. Raw data flows straight into Apache Kafka for high-throughput streaming ingestion. From there, it's picked up by Spark structured streaming for micro-batch processing. The clean data gets stored in an HDFS Parquet data lake. Then the analytics layer kicks in, utilizing GraphAX for the network analysis and a dedicated differential privacy layer to make sure all the published results are completely secure and handled responsibly. To make this whole pipeline lightning fast, we leaned heavily into some incredibly clever probabilistic algorithms. Let's start with the Bloom filter. Think of this guy as the ultimate hyper-efficient bouncer at a nightclub door. As millions of flight records stream in, this algorithm instantly spots and rejects duplicate records. And the best part? It does it without needing to maintain an expensive, memory-hogging guest list of every single flight it's ever seen. Next, we've got HyperLogLog. Imagine a genius statistician who can stand on a balcony overlooking a massive stadium crowd and highly accurately estimate the exact number of people down there without actually counting every single head. That's exactly what HyperLogLog does for cardinality estimation. It counts the number of highly unique flight routes using what's called sublinear memory, which saves vast amounts of compute power.
Then there's the CountMin sketch. Basically, this is your relentless frequency tracker. Its only job in the world is to continuously monitor the stream and keep a running tally of the worst offenders, the heavy hitter tail numbers and the big delay hubs. It absolutely never forgets them, and it does it all while using just a fraction of the memory that a traditional database would need. Now, what about grouping singular flight routes? For that, we used min-hash locality-sensitive hashing, or LSH. Traditional systems would try comparing every single route to every other route. Yeah, computationally impossible at this scale. Min-hash acts more like a fingerprinting system. It converts complex routes into super compact signatures so it can instantly group similar delay behaviors together.
And finally, the crown jewel of the analytics layer, Spark GraphX PageRank. Yep, this is the exact same mathematical algorithm Google famously uses to rank the importance of websites across the internet. But here, SkyRipple is applying it to airports. It measures an airport's systemic influence over the entire aviation network, rather than just passively counting its localized delays. So why go through all this trouble with these algorithms? Because if you try to use exact counting methods on 7.2 million streaming records, your system will literally crash under the massive memory overhead. But by using these probabilistic data structures, we achieved a stunning reduction in memory footprint. We dropped memory usage by over 99%, while still keeping the accuracy incredibly high. Honestly, it's absolute engineering magic. All right, let's look at the results and see what this actually tells us. When we fired up that PageRank algorithm, the network superspreaders lit up immediately. Unsurprisingly, the massive, highly connected hubs topped the list, right? Chicago O'Hare, Atlanta, Dallas-Fort Worth, those are your primary engines of delay propagation across the country. But here is the genuinely surprising part. Number 4 on that most influential list? Denver. DEN. Now, Denver isn't always the highest in raw delay volume, but because of its highly specific geographical and structural position in the network, it acts as this hidden amplifier. A delay in Denver ripples out and impacts a completely disproportionate number of downstream airports. This basically proves that network centrality matters way, way more than just raw delay counts. Let's rapid-fire some of these hard results just to prove how rock-solid this system is. When we validated against official historical FAA data, SkyRipple's network modeling hit an 85% precision rate. Operationally, the streaming pipeline held a deterministic throughput of 1,400 records per second across 141 streaming batches. It cleanly handled a 13-time scale-up from the validation tier to the full dataset, and it did it without a single out-of-memory crash. Just to recap those numbers, because they are important, 85% FFA precision, 99% memory reduction, 1,400 records per second throughput, and seamless 13x scalability. But it's not just fast, it's secure. By adding an epsilon-controlled differential privacy layer, SkyRipple lets airlines and researchers publish safe, aggregate statistics. In fact, when we ran adversarial audits, they showed only a 50.8% attack success rate at an epsilon of 1.0. That proves the data genuinely stays private. Now look, building a production-ready pipeline like this isn't all sunshine and rainbows. We earned some real engineering battle scars along the way. And I want to show you these challenges because it proves that this pipeline wasn't just built in theory. We genuinely stress-tested it under severe constraints. We hit 3 major walls. First, the dreaded garbage collection death loop, where massive memory pressure just froze the Spark executors. We solved that by swapping expensive operations for native broadcast variables. Second, the Catalyst optimizer actually hung for over an hour evaluating rules. We smartly bypassed that by forcing a broadcast inner join, cutting the runtime down to milliseconds. And finally, running this on a MacBook caused thermal throttling that dropped network heartbeats. We had to build custom, hardened network timeout configurations just to keep the cluster alive when it got too hot. So, why does all this technical heavy lifting actually matter in the real world? Well, it's a total paradigm shift. It means airlines can finally move from just reacting to delays to proactively managing hub scheduling based on real network intelligence. It means the FAA gets incredibly accurate but entirely privacy-safe aggregate statistics. And it hands the wider research community a fully reproducible, open-source big data reference architecture. SkyRipple proves that when you combine network thinking with streaming big data tools and responsible privacy-preserving analytics, you can illuminate exactly what traditional systems are completely missing. You can literally track the contagion. Going from raw flight records to actionable network intelligence, that is exactly what big data engineering is built for. The tools are right here. The real question is, are we finally ready to cure the viral spread of flight delays?